In late 2024, Earth temporarily captured a tiny, fast-moving space rock known as PT-5. But as it turns out, we have another companion out there, an asteroid named 2025 PN7. PT-5 was a fleeting guest, making a few laps over 2 months before leaving. PN7 is different. It measures barely 62 feet across, roughly the length of a bowling lane, and it has been silently keeping pace with us for 60 years. If a 60-foot rock is traveling right next to us for decades, why can't we see it in the night sky? And how has it managed to avoid crashing into the atmosphere? Understanding exactly how these rocks stay so close requires us to look past the visible light in the night sky and map the invisible gravitational boundaries surrounding our planet. Look at the heavy, permanent craters on our actual moon. It sits roughly 239,000 miles away, safely within a zone of space where Earth's gravitational pull exerts absolute control. This boundary line represents the Hill sphere, a 1 million-mile invisible bubble where Earth's gravity overpowers the Sun. Watch this tiny dot, representing asteroid PT-5. Fast-moving rocks can pierce this bubble, get caught by Earth's gravity for a few laps, and briefly become true mini-moons. Because of their high speeds and low mass, they always slip out. Any object claiming to stay with us for 60 years cannot be inside this bubble. Step outside that 1 million-mile boundary and the physical rules change. Out here, millions of miles into the deep solar system, the Sun's gravity completely takes over. Notice how the asteroid dot moves perfectly parallel to Earth around the Sun. Astronomers call this a 1-to-1 resonance. But from our point of view, because the rock's speed varies slightly, it creates an optical illusion. It draws lazy, scribbled loops, looking like a satellite. These objects, known as quasi-moons, are completely independent solar orbiters. We just happen to be running a marathon at the exact same speed. That synchronized pace is just one behavior inside a larger family of rocks known as co-orbitals. These are objects that find themselves permanently caught in the constant, immense gravitational tug-of-war between the Earth and the Sun. This horseshoe orbiter trace forms an enormous U-shape, swinging ahead and behind Earth. Further out, 60 degrees ahead and behind us, are Lagrange points, areas of balanced gravity. Here, Trojan asteroids hide in bean-shaped loops, while erratic jumping Trojans slowly drift between the two zones. Earth's orbital path is a highly structured, chaotic highway populated by a network of trapped gravitational hitchhikers. The physical makeup of a quasi-moon named Kamualewa provides a direct window into where these strange tagalongs originate. Take a look at the rough, porous texture of this Apollo lunar sample. When astronomers analyze the light bouncing off Kamualewa, it matches the chemical reflection of basalt rocks exactly like this one. That matching signature suggests these specific quasi-moons are actually ancient shrapnel, violently ejected from our actual moon during a prehistoric impact. Because they ride right next to us on the orbital highway, reaching them requires remarkably little rocket fuel. They offer practical stepping stones for deep space missions. A true moon exerts physical power over a planet, driving violent ocean tides and locking Earth's tilt firmly in place to stabilize our seasons. These tiny, hidden rocks cannot do that. But by studying their long, synchronized marathon with Earth, we gain invaluable maps to navigate the chaotic mechanics of our cosmic neighborhood.